we're looking at rust and galvanizing. Right, okay. Let's take that. Right, iron is a useful metal. One problem with using iron is it can rust. Name the iron compound present in rust. So if you iron, water, and oxygen, you end up with rust. And rust is known as, right, I'm going to write the full name out. Hydrated iron, and then 1, 2, 3 oxide. Fe2O3. Let me just go through that. Fe 3 plus iron, oxygen 2 minus iron, because the numbers are not the same. Remember, we ignore the signs and we simply cross over. There you go. So then it becomes Fe2O3. So that's iron 3 oxide, hydrated iron 3 oxide. You don't need to write that. You don't write iron oxide. There's a danger you could lose the mark. So we could write iron 3 oxide. There you go. Name 2 substances that iron reacts with when it rusts. Oh, right, so what we've said is up here, oxygen and water. What type of reaction occurs in the rusting of iron? So what you've got is, you've got iron plus oxygen gives iron 3 oxide. Forget trying to balance it. Because iron has gained oxygen, it is called oxidation. So it's that one. Right. Galvanizing is, right, there's iron. You put a layer of zinc on top. And that stops. The whole idea is that it's a barrier. It is a barrier against oxygen and water. That's what it is. Right, so identify the other metal, zinc or Zn. Identify one suitable object suitable for galvanizing. Right, bicycle chains, you tend to put oil on there or grease. Car engines needs oil. Drink cans don't need anything. Well, drink cans are normally made out of steel or aluminium. And bucket. Okay. State 2 of the methods of preventing iron from rusting. So you could oil, grease, you could paint it, you could cover it with plastic, or you can cover it with another metal, either magnesium, blocks, magnesium blocks. This is more for hulls of ships. And what else is there? Yeah, I think that's enough. Right. What is needed for iron to rust? One of the substances for iron to rust, we said oxygen. You could put air, but it's safer to put oxygen because if they get a bit tight on the mark scheme, air might not cut it. State the name of this compound formed. So this compound here, it's a brown compound, right? It'll be, I remember what said, iron, 1, 2, 3, brackets, oxide. Don't just put iron oxide. They've also said in the mark scheme that you can get away with ferric oxide. But to be safe, to make sure that it goes across all exam boards, stick to iron 3 oxide. Right. So you've got 3 students investigating the rusting of iron nails. They measure the mass of each nail before placing it in some water. After rusting occurred, the nails were removed and their masses were measured. So before it was 3 and it went up to 3.3. 1.5, it went to 1.7. 1.8 and it went down. Okay, that went down. Just one problem in measuring the mass of a nail after rusting. Because the nail is wet, you might end up measuring the water as well as the oxygen that is gained through rusting. Nail has water on it. Student A thought that the result showed that his nail had rusted the most. Student A, right, yeah, because this has only gone up plus 0.2, that's gone up plus 0.3. And this has actually gone down 1. And it increased the increased in mass the largest amount. Student B thought that results showed that her results were most. Right. As the proportion, so look, if I did 0.2 divided by 1.5, that is bigger than 0.3 divided by 3.0. So it has increased increase more as a proportion or as a percentage. Well, write the word percentage. There you go. How do the results of student C show must have made an error in his experiment? Because yeah, the mass decreased. Because when you're gaining oxygen, it should increase, but it's decreased. So there's been an error in either measuring in the first place or at the end, or some rust might have fallen off, we don't know. Right? Most methods to prevent rusting, they use a physical barrier. This keeps out water. Complete the table, right? A bicycle chain, I would use oil or grease. A railway bridge, I would paint it. That's the cheapest way. And you see these guys. So there's the bridge, metal bridge, and they're sort of like hanging off. They're sat there merrily, like this, with the legs dangling down, and they're painting away. And then by the time they've got to that, they'll have to start again, especially on super large bridges. They start again. Some iron objects are coated with zinc to prevent rusting. The zinc acts as a physical barrier, but an extra advantage of using zinc is that it continues to prevent rusting even if the layer of zinc is damaged. State the name of this type of rust prevention and explain how it works. Right, the name of this is called, galvanizing. It's called galvanizing or sacrificial protection. Right. Since or because zinc is more reactive than iron, zinc reacts with oxygen to to be oxidized instead of iron. There you go. So 1, 2, 3. Right, okay. Aluminium and iron have similar properties. Malleable, that means you can bash it into sheets. Ductile, good conductors of electricity, good conductors of heat, have a high melting point. Choose 2 properties that make iron suitable for metal saucepans. So it's high melting point. And we can say good conductors of electricity. There you go. Aluminium used as a power cable. Right, first of all, it is, you can say it's ductile, and it can conduct, good conductor of electricity. Right, steel is an alloy. There are 3 differences between steel and aluminium. Steel can rust, steel has higher density, steel is much stronger. Why is steel better? Because it is stronger, because you're going to put loads of weight on the bridge. Why is aluminium better for making aircraft bodies? Right, because it is less dense. It's the opposite, and it avoid what do you call it? Corrosion. So it's lower density is the most obvious one, because you're going to fly, aren't you? Lower density. Aluminium has a lower density than steel. Okay. Right, the reaction between aluminium and iron 3 oxide is known as a thermite reaction. Thermite, when you see the word therm, think of heat. Right. So you've got magnesium ribbon, mixture of aluminium powder and iron 3 oxide, and you've got sand. The magnesium is lit, so you light that to ignite the reaction mixture. The reaction is highly exothermic, so this will start giving off loads of heat. That means it's exothermic, yeah. The equation is 2Al plus Fe2O3 gives Al2O3 plus 2Fe. So have you noticed iron here is on its own, so it becomes just a metal formed on its own. What is the term exothermic? Exothermic is when a reaction gives off heat to its surroundings. There you go. So what does that tell you about the reactive aluminium if it kicks out that? So look, please stop losing careless marks always. And then I think of chicken, CH, so that's carbon and hydrogen, and zoo is copper, silver, oh, gold. This here, these three are in the periodic table straight after each other. That is potassium, sodium, lithium, calcium, magnesium, aluminium. Right, this is carbon. It's a non-metal. Zinc, iron. This is hydrogen, non-metal. Copper, silver, gold. So this here is the reactivity series. Okay. Right. Aluminium's here. Iron is there. Because aluminium displaced iron, we know we know, right, aluminium displaced one second, right, displaced aluminium displaced iron okay, from its oxide. This is the full way. Why? Because it is more reactive. That's where your second mark's coming from. And we know that from there anyway, but they're asking you about what happens in the actual. Which element is oxidized? Right. You have aluminium plus iron oxide. Aluminium gains this oxygen. So aluminium is oxidized. So, right, why so? No, because why do we say it's being oxidized? Because it gains oxygen. There you go. Right, so this is what goes on. So you've got a rail, and just say if it's damaged here, we need to melt it and repair it. So you ignite the aluminium powder, it produces loads of heat, melts the iron pours into there, and then you've got a joint between the two rails. why iron produced in the reaction is molten, right? Because the temperature of the reaction, reached is greater than, or equal to, yeah, more than, you say greater than, more than, or even equal to, oh, equal to, it has to reach the boiling point and then it'll melt, equal to the melting point of iron. Right. Right, okay, let's do this one. We can do this one. This is doable. You've got iron wool here. You've got a measuring cylinder. You've got 100 centimeter cubed of air. Remember we said air is a mixture. What does it consist of? Nitrogen, oxygen, argon, carbon dioxide, amongst other things, water vapor and so on. But these are the main bits that stand out. 78, 21, 0.9, 0.04%, and so on, right? That's what it is. Right. After a week, the oxygen is being used up, so it's dropped to 80. So that's why the water level's gone up. After another week, they measured it and it's remained at 80. That means any oxygen that was in here has been used up. There's no more oxygen in there, so there's no more reaction taking place. So there's no more rusting. Reaction stops. Right. So with this, we need to explain why that was. So iron reacted with oxygen, and then after 2 weeks, after 2 weeks, no decrease, because why? All the oxygen has been used up. Done. Because there's no more oxygen, so there's no more iron oxide being formed. Right, again, this is a little typo. Right, okay, it's playing up again. Not a problem. Okay, let's try that. Yes, it's working now. That's good. Right, okay, there you go. So iron plus sulfuric acid gives iron sulfate and hydrogen. So iron plus sulfuric acid gives iron sulfate and hydrogen. You could also put iron to, let me write that properly. You can write that as iron to sulfate. Right, there you go. Aqueous sodium hydroxide. So whenever you see the word aqueous, you're going to think of water. Right. So you add aqueous sodium hydroxide. Right, okay, so we need to know the colors of iron 2 plus ions and iron 3 plus ions. So I remember it as a green leaf in spring and it becomes a brown leaf in autumn. So it goes from green to brown. Okay, right. Ooh, right, okay. So I've got to be careful with that. So I've got to write down green precipitate. So a little bit of solid. And you've got brown precipitate. Right, okay. You have iron, you coat it with zinc. That have you noticed here? The zinc barrier has been broken. Then what happens is, let me just draw that out. So that's zinc, and this is iron. This is zinc. Now what happens is water and oxygen can get in. Water and oxygen can get in. So what happens is you'll end up with iron reacting and you'll end up with zinc reacting. But what it is because iron is more reactive, let's have a look. No, zinc is more reactive. Sorry, zinc is more reactive. I'm just trying to think of that. Please stop losing careless marks always. Chicken, CH, and then ZI. So yeah, zinc is more reactive than iron. So because zinc is more reactive than iron, zinc will react with the water. No, sorry, with the oxygen. It doesn't react with the water. I'll take that back. Although water is present if iron was to rust. To become zinc oxide. So it forms a layer of zinc oxide. So it stops the iron rusting. So it sacrifices itself. The process is called galvanizing. So that's what happens. Right. 3 pieces of iron are left in trough. Does it say up there? Yes, it does. Right. When you get a brown solid, the common name is called rust. Right. Identify 2 substances that react with iron to form. Right. So it's oxygen and water. Water. Okay. Explain with reference to the symbols in the box why the brown solid does not form on C. Where is C? Right, okay. Right. We can say that zinc is more reactive than iron. So zinc loses 2 electrons to form a zinc 2 ion and stops iron from forming a Fe2 plus ion. Okay, that's a weird one, but let's keep going. We've got, okay, we haven't got much. Right. The iron from the blast furnace contains about 10% biomass of impurities. 2 impurities are carbon and silicon. The diagram shows a method to decrease the amount of carbon and silicon. So your oxygen and powdered calcium oxide is put in there. Molten slag is the waste that we don't need. In there. Molten iron from the blast furnace. Right. Oxygen converts carbon and silicon into their oxides. Write a chemical equation for the reaction between carbon and oxygen to form carbon dioxide. So carbon plus oxygen. We know oxygen comes in pairs. It is diatomic and it gives carbon dioxide. Right, we've got one carbon, yeah, done. All right, okay, that's it. Right, what type of reaction is silicon oxide and calcium oxide? Silicon oxide and calcium oxide. It's a neutralization reaction. Yeah, you just got to know that. It's not combustion, it's not decomposition, and it's not redox. Right, let's keep moving on. One problem using iron, 2 substances that must be present. So you see, this keeps repeating itself. Oxygen and water. One method of preventing is to paint it. Suggest, right, what this does, it prevents oxygen and water coming into contact. Coming into contact with iron. Right. You can protect it from rusting by coating it with zinc. Remember, this is called galvanizing. Right. We've said this. How does this work? So we need to explain how this method works. So first of all, you write zinc is more reactive. So it's only a 2 marker, so it's not as detailed. It's more reactive than iron. Right, iron, I-R-O-N. Right, so loses electrons more easily or readily. So corrodes instead of iron corroding. There you go. Right, aluminium is extracted from the oxide using electrolysis. Why is aluminium not extracted? Right. Because aluminium, right, in the reactivity series, look, aluminium is there. right? Carbon's there, zinc, iron, and hydrogen. So aluminium is more reactive. So the reactivity goes down, it decreases. Okay. Aluminium is not extracted by heating its oxide with carbon monoxide because aluminium is more reactive than carbon. Why is iron not extracted from its oxide using electrolysis? Because energy costs are too high. Right, that's it. That is rusting done. Galvanizing.